Hi everyone. So today we're going to be doing day 2. Let me share my screen with y'all so you know what I'm talking about. All right, should I do British accent? I was doing north, now south last time, but you know. All right, so as you can see on the screen, we have some important information. So make sure that you are keeping up with your notes. We're doing day 2 today. Excuse me. I don't have corona. Cut it out. All right. So you can, if you got a packet, that's great. Do it on the packet. The packet's also on Edmodo where you can print it out. If you can't print it out, do it on loose leaf. The whole point of it is that you get it done, right? Make sure you join Google Classroom because that's where I'm putting all the classwork. The classwork for day 1 was on there, and the classroom assignment for day 1 was due yesterday at 5 p.m. So that's what I'm going to do. I'm going to give you guys until like 5 p.m. that day. But I might just I'm just going to have everything we do on Friday because of just to make sure everybody has time with like the technical difficulties and whatnot. So your codes are there. Periods 3, 4, 5, and 7 are in yellow, and periods 2 and 6 are in green. Let's keep it going. All right, so important information. Make sure that you're following the class Instagram, the Remind. I'm like anything I announce is gonna be on the class Instagram and Remind. The assignments are on Google Classroom. The Edmodo code is right there. It's CQAGFD, all right? So announcements for upcoming due dates. I know that this is kind of a confusing time because you might not be able to like ask your questions face-to-face with your teacher. However, I'm trying to make it clear. I'm going to also have office hours today, Tuesday, March 17th, around 11, all right? So let's see. Okay, so notes for Unit 10, we're going to say that they're due March 30th and 31st. After we're done with the unit, you'll have a small quiz at the end. Once we're back, if we're not back yet, we'll figure it out, like play by ear, adaptability, right? All right. So remember, coming up, start your flashcards, start learning that vocabulary. Chem Blitz, Unit 10. If I have to like chat with you via the Instagram Live to test you, I will, right? All right, so I'm assigning a short independent practice for each day. It's not as long as it would have been if you were in class, because I understand that everybody is probably, you know, getting work from other classes, and it's not how much you do, it's whether you get it or not, right? And if you have questions, make sure that you ask me. I always make myself available, so let me know. And do these by the respective due dates, right? So Unit 10, Day 2. All right, so Daily Catalyst. I'll give you guys some time so that you guys can work on it. We learned Day 1 yesterday, so let me open up my notes. So we went over Day 1 yesterday, right? What is kinetic molecular theory? So this is what I was talking about, saying it's a theory that describes the behavior of matter. So based on the following assumptions, right? That particles are spherical, so they're in a sphere shape, and they're solid objects, and that they're in constant motion, they're never still, and the kinetic energy of particles changes depending on the temperature, right? So if you have higher temperature, you're gonna have more kinetic energy, right? So label all phase changes on the diagram below. Circle the phase change that absorbs energy. So if we were to label all the phase changes on, okay, so this is exactly what we were going through yesterday, right? Let's see if I can, you know, text right on there. All right, so right here, going from solid to gas, that is going to be sublimation. All right, going from gas to solid, that is deposition, if I'm not mistaken. Yep, deposition. Where to go? Liquid to gas, that is evaporation. Gas to liquid, condensation, right? So these are like the phase changes that we talked about last class, and what we talked about at the beginning of the year a little bit, but we talked about it more in depth last class, right? So solid to liquid, that is melting. Liquid to solid is freezing. All right, so if you have any questions, remember office hours at 11, tune in. All right, it's like, let's see. Okay, so label all the phase changes on the below diagram, circle the phase changes that absorb energy. So remember, absorbing energy, right? When I made that chart yesterday, I said melting, evaporation, and sublimation all absorb energy. The ones that release energy are freezing and condensation, right? So if we were to circle, melting, there we are. Don't make fun of my circles. Evaporation, and sublimation. All right, don't judge them. I'm good. All right, so how do attractive forces affect the shape and particles of spacing of solids, liquid, and gas, right? So let's see. So that's like those images that I was saying, like solids have strong intermolecular forces and they're like really tight together, kind of like this. This is like a solid. Like if these were all particles, they would be all tight together, right? And then for liquids, they're slightly strong, but they're loosely packed. So let me see. This is all my roommate stuff because she is also teaching from home. She got a whole bunch of crayons on here, so let me just borrow them for a little bit. All right. So like if we were liquid, maybe do some tips. Like then you have like a whole bunch of crayons just being like loosely spaced out. My bad. They have more space between each other, right? And then for gases, gases are just like free. They're just like all over. Wait a minute. Let me put these crayons back or break one. No, okay, that'll be fine. So gases are more like, if I was to draw them, they would look like this. So they're all spaced out, right? Can you see that? So let me see if I can actually, because I have my cute little chart paper up here, you know, like behind me. So if this was the gas phase, right? And this is the container it's in, right? Whatever, like, well, like they, you see? Y'all can't even see it. I'm done. Let me use more. Correct it up. Okay. Oh, some technical difficulties. All right. So if it was the gas phase, the dots are spaced out, right? They're, wow, you really, I'm crying. Okay. Give me a second. We use a dark color. So. Okay, so there we go. It's a lot easier to see. Don't judge my drawing skills. It's not my wall, it's a copy paper. But it's the gas phase, so the particles are spaced out, all right? Moving right along, back to my seat. Okay. And those forces are weak because they're far apart, right? All right, so for number 4, it says sketch a heating curve and label the phase of matter. Circle the points on the curve where kinetic energy is increasing. All right, So for this, we just saw how that was difficult to sketch. So I'm gonna find a picture of a heating curve in a previous what's it called, slide. All right, where'd it go? No, put the text to stop drawing. All right, did it stop? All right, no, why am I continuing to draw? No, stop drawing. All right, no, now I'm putting X's on, I'm done. Okay, okay, the mouse finally. You know, technical difficulties, still trying to figure this whole thing out. Oh, well, how do you erase this? Because it's not cute. Okay, there we go. Okay, mouse. So the heat chain curve, right? Where'd it go? So the question was, sketch a heating curve. So I'm going to show you guys a heating curve, and we're going to label each phase of matter and circle the points where the kinetic energy is increasing, right? So heating curve, where you at? Come on, all right. Loading. All right, heating curve. Okay, so this is what a heating curve looks like, right? So we said that, okay, the temperature is low on the left side, and it's always going to start off like the incline is going to be a solid, right? Then when you have it be parallel, that's when it's going from solid to liquid, right? So C is going to be solid to liquid. That's the melting point. Then C to D, that's another diagonal, so that's going to be all liquid. Then D is going to be a point where it's going to become change from liquid to gas. So that's the evaporation point. And then like, how do we know? And then it ends with gas again. So how do we know whether the kinetic energy or potential energy are increasing or decreasing or whatever, right? Well, for heating curves, they're always increasing. For cooling curve, they're decreasing. Kinetic energy is always like when you remember like what I was giving you the examples of solids, liquids, and gas. So which one's gonna have the most kinetic energy? The higher temperature, it's gas, right? So when they're making that change from like solid to liquid or liquid to gas, like that's where potential energy increasing. But whenever they're in that incline, so like solid phase, liquid phase, gas phase, that's when kinetic energy is increasing, all right? Just a little review of what we did yesterday, all right? So we went over the do now. Okay. Let's see. Oh, I'm crying. I could just use this example. All right, so you performed an experiment and recorded the following data. Draw a line graph on the right, label both axes, and give the graph a title. All right, so let's say you got this data. You have to choose an X and a Y axis, right? So time is X axis, temperature is Y axis, your title is temperature versus time. All right, then you plot your points on the graph. So -20, 0, 0, 5, 0, 10, 100, 25, 25, 100, 40, 100. Okay, so we have our, it's gonna be a heating curve. So connect the dots. All right, so where on the graph is the substance liquid? So remember, our first diagonal is solid. This part right here, let me just, I'm pointing into it like y'all can see that. So this part right here is a solid. This is a solid. Wow, this takes so much concentration. Solid to liquid. This is the liquid, and then liquid to solid. I mean, not solid, gas. Okay. All right, so it's asking which on the graph is a liquid. So that liquid would be that diagonal, and that would be this part, right? Okay, let me erase all this nonsense. All right. Where are we doing? What's going on there? All right. So, is it occurring? Okay. Oh, there we go. So it's that part where the arrow is pointing. All right. So this is the picture I drew. No, I'm kidding. So draw a particle picture of salt dissolving water. So you got salt, NaCl, Na is plus, Cl is minus. You know, that's salt. We get a prop. And then you have over here, if you put it with water, the positive particles of the water, so the H plus, are going to be pointing towards the negative Cl. Like right here. Oh, my bad. Like this one is positive, this is negative. That's why they're pointing towards each other. Whereas over here, that positive right here is connected to this negative, right? Which is oxygen in water, right? Okay. Okay, so let's get started with the notes. All right. So day 2 of your note packet. All right. So we already did the quick review. So let's start talking about solutions. So a solution is a homogeneous mixture composed, let me just move this, of a solute and a solvent, right? So a solute is a substance that dissolves. So we have used this in class before. This is copper sulfate, I believe, yeah. And then let's say this is water. So the solute is the substance that dissolves, that would be the blue. And then the solvent is the liquid that can dissolve other substances. So that would be the water, right? A substance that is able to dissolve in a solvent is considered to be soluble, right? So if it's non-soluble, that means when you put them together, they're not dissolving. It's just going to be liquid and some powder inside, all right? So let's see. Perfect. So you got solute, solvent equals solution. So solute is the solid, solvent is the water, then your solution is this clear blue liquid. We have done this in class, in a little experiment, I believe, right? Let's keep it moving. It's little technical difficulties. All right, so for the demos, I'm actually going to be adding videos of this because I do not have styrofoam or acetone, and you know, I tried to get some, but didn't find any. All right, so I'm gonna put videos in there so we know what's going on. So I'll put those in first, and then I'll go through this. Okay. Okay, so now that you saw the videos, let's quickly review. What did you observe? What happened to the styrofoam cup when you put styrofoam and acetone together? It dissolved, right? It turned into simply plastic. What's the solvent in this experiment? Is it the styrofoam or is it the acetone? It's the acetone, right? So the solute would be the styrofoam, and remove this. You got the acetone is non-polar, right? So, and this styrofoam is also non-polar, right? So we'll quickly learn that like dissolves like. So they were able to dissolve because they're both non-polar. Styrofoam and water, if you're taking takeout, you got your food and then it starts pouring, it's never dissolved on you, right? It's literally just wet styrofoam. So what did you dissolve? What did you observe happen to the styrofoam cup? The styrofoam just floated. It's not going to catch fire or anything. What is the solvent in this experiment? The water, right? So the solute is a styrofoam. Water is a polar, non-polar. it's polar. And the styrofoam, like we said, is non-polar. So those are not the same, right? Polar, non-polar, they're not the same. So they're not going to be dissolving, all right? So salt and water, all right? So y'all have been, like, y'all might have done this at home. I'm cracking up with my accents. Okay, so what did you observe happen? Let's see if I can do an Irish one. So, my accents are so... All right. Okay, so what did you observe happen to the styrofoam cup with salt and water? So inside, it would just be like salt dissolve, and right, and then you put salt and some water, it dissolves, right? So the solvent is water, solute is salt, water is polar, and so is it should say salt here. Oops, typo. Excuse that for a second. Where'd it go? Yeah, this should be. There we go. No, not salt. All right. Okay. Moving right along. All right. So polarity. Like dissolves like I alluded to earlier. So polar solvents dissolve polar solutes. So what that means is polar, they're going to dissolve. Non-polar, they're going to dissolve. So non-polar solvents dissolve non-polar solutes. So you see my little image right here. Oil is non-polar and water is polar. So when you put them together, you notice that they don't mix, right? They don't dissolve in each other. They're not alike. So there's going to be a layer of oil and a layer of water. If you look at my image right here, you remind me of me, so I like you. That's a nice way to remember it, right? Okay. Moving right along. Okay. So solubility, this little tab, yeah, I'm feeling some type of way. All right. So solubility is the amount of solute that dissolves in a solvent at a specified temperature. All right, so that's a lot of words. What does that mean, right? It basically tells you how solute can dissolve in water in solvent. So there's three types. So there's three types of solutions. So you have an unsaturated, a saturated, and a supersaturated. We're going to go into each one of them. So let's get started. All right, so unsaturated, that means like more solute can be dissolved. It's not yet saturated, so it has maybe like a dot here, a dot there. You still have the ability to dissolve more, right? So that would be like if you put like in a cup of water, if you had, it'd be like this, right? It's my coffee from this morning. So if I just put like a grain in one little thing of sugar, it's not gonna be saturated. It could still take some more sugar, right? It's about to be bitter. All right. All right, so all solute particles have dissolved for an unsaturated, but it can still dissolve more, right? So where that? Saturated. So that means it contains the maximum amount of dissolved solute for a given amount of solvent, but so what does that mean? Like no more solute, like it means like Miss Vargas went, put some sugar in here and like it's saturated, like it has the maximum, no more solute can be dissolved. If I continue to put sugar in this, it would be like super saturated, meaning like sugar is going to be at the bottom. Okay, so super saturated contains more solute than a saturated solution. So like I said, you would have residue at the bottom, right? So graphing a graph. So on your notes, you should have already filled this out, filled this out. Pretty much everything except this little square over here. All right, so solubility graphs. So circle the substance most soluble at 10. So how do we read this? It's just like, this Vargas is bugging out because it's so much stuff, right? So we're gonna learn to decipher it together, all right? All right. So circle the substance most soluble at 10 degrees Celsius. So let's look down here. We find the temperature. 10 degrees Celsius is over here. Which one is the most soluble? So solubility is over here on 10 degrees Celsius. Which one is most soluble? Oh, is that you, NaNO3? It is. Oops. It is NaNO3, right? So that's how you read this graph. It's temperature versus solubility. We look at the temperature, it's asking for the most soluble, so it's right above, right? Okay, moving to next question. Circle the substance least soluble at 90 degrees Celsius. So now we gotta go to 90 degrees. Where are you at? 90, right here. Least soluble, so it's the one lower, closest to the bottom, right? Which is my cesium sulfate. Y'all are like, cesium? She's making it okay, so am I correct? There we go. Yep, I am correct. Cesium sulfate. Okay, so let's keep it moving. I think it's 2 more questions. Oh. Right. There we go. So 30 grams of KCl3 is dissolved at 70 degrees Celsius. Okay. So what? Is the solution saturated, unsaturated, or supersaturated? Well, let's see. It's a lot of info. So let's go to 30. So it's saying 30 grams of KCl3. So, and we got, so let's look at 7. So it's telling us 30 grams and 70 degrees. So let's find that 70 degrees on here. It's right here, right? And then our 30 grams is right here. So if we trace it up and trace it up on both sides, we see that it intersects. So, oh, no, Siri, what are you doing? All right, so the solution is going to be saturated because it's perfectly on their intersection. And that means that it is saturated. Okay, so let's say that it wasn't, right? And like it was right below, like it was right here. So this means like this line shows you like that's when it's saturated. If it's right below, that means it's not unsaturated. If it's right above, it's supersaturated, right? Oh, it's Mona Lisa. There we go. Okay. All right. So like I said, above line means supersaturated, below line means unsaturated. Last question. So what happens to solubility as temperature increases? So what have you noticed? As the temperature goes up, what happens to solubility? It also increases. The relationship is proportional. So if one goes up, the other goes up, right? So to do by 5 p.m. today, March 17th, independent practice on Google Classroom, right? So it's a Google Doc now, so feel free to print that out or do it on a notebook. The whole point of it is that you get it done, right? It's not a lot. Usually I give y'all front back stapled. It's just 1 page. All right. So another thing, office hours. So I'm going to be on a Zoom call. I'm going to put the link up on the class Instagram and send it to Remind at 11 a.m. just so I can clear things up, you know, join if you have questions. You just miss me in my class. Or I just want to go over some examples. just review anything about day 1 and 2, right? I love y'all. This is probably what we're going to be doing, answering some questions about like you may have, briefly going over day 1 and 2, going over some more examples. All right, so I hope you can tune in. If you like what you saw, like subscribe below. Just kidding, you're in my class, you have to watch these. I'm just kidding. All right, so I love y'all. Stay safe. Wash your hands. If you have any questions, feel free to let me know. All right. How do you turn this off? Okay, let me stop sharing.